Hi, good afternoon, everyone. My name is Peixin, and I'm from University of Maryland. And it's my honor to be here and present our work on a semi-trust inference framework for trust-aware social recommender systems. So our work mainly focuses on the scenario of social recommenders. And the motivation is that nowadays, social networks, they're becoming more and more popular, and they're just becoming new venues for advertising and marketing. And currently, a lot of recommenders, they just integrate signals from a social network to provide better personalization and recommendation. And one type of a social recommender is called trust-aware recommender system. It is an important application as a trust signal is extracted from the social connections for the recommendation. So in terms of challenges, so apart from some common challenges shared with other social network-related applications like sparse connections and data availability, because of the special property of trust, especially in this trust-aware recommender system, it has the challenge of inconsistency and conflicts in trust opinions, as well as the nonlinearity in trust formation. So here, today, we will not talk about the trust-aware recommender systems. Instead, we will focus on how to address the challenges mentioned above. And as a general approach, trust inference is used to address all these challenges. And most trust inference algorithms can be categorized in two groups, namely graph theoretic models and machine learning approaches. So in graph theory models, they generally have good performance in terms of efficiency and reasoning. But meanwhile, it has because it's more in most cases it's a linear approach. So the nonlinearity in decision making is not well captured, and also it's very sensitive to connection sparsity. And in terms of accuracy, in general, it's not that accurate compared to machine learning approaches, which are data-driven and based on features extracted and also the observation over the training data set. But based on the machine learning algorithm used, it can be very slow in speed, and also sometimes it can be really weak in interpretation. So here, we come up with an idea to use an algebraic approach to on one hand, handle the nonlinearity and the conflicts in trust, but meanwhile get a very efficient solution with very high accuracy. So here's our high-level idea. So our idea is trying to transform the intuitive heuristics into formal modeling. And think about the case when you want to get some information about some people you don't know and may be far away. I think the first thing you will think about is to ask your friends about their opinions about that person. And if your friends, they know about him or her, then they will tell you about their information. But if they don't know, the most possible case will be they will ask their friends to solve the problem. So this process can be decomposed into two parts, the trust propagation and the trust aggregation. But if we consider the distrust, the existence of distrust, as well as the nonlinearity and the conflicts in trust we mentioned before, actually this modeling process is non-trivial to approach. So here, in order to have a good model to handle the distrust part and also the nonlinearity in decision making, we come up with this idea to use a semi-ring model. All right, so as a brief introduction, semi-ring is actually an algebraic structure that defines on the set with two operations, addition and multiplication. And it is well developed in constant satisfaction problems. And here, in our semi-ring model for trust inference, we are trying to connect the trust aggregation process with the additive operation and the trust propagation process with the multiplication process. All right, so before implementing our semi-ring model for trust inference, I'll briefly introduce our trust model. And in our trust model, the trust is defined as a two-dimensional vector that contains two information. The first element in the vector is the trust information. It basically describes how much you trust the other person, or how you think about the other person. So if you really like that person, then the value should be positive. And if you don't like that person, then it should be negative. It's quite natural. And the second element we call the certainty. It basically describes how certain you are about your trust opinion. So if you have a lot of interaction with that person, then definitely your trust opinion is very confirmative. You're sure about your idea about the other person. But on the other hand, if you don't have a lot of interaction, then in most cases, even though you have an opinion about that person, you won't be very confirmative, and the certain value can be very low, and as low as very close to 0. And so based on this, definition of trust opinion vector, actually a trust network can be established. And here we show like actually user is represented by a node in the graph. And for each edge represents the trust relationship, directly trust relationship between two users. And associated with each trust relationship, there's a two-dimensional trust opinion vector. And again, the first element represents trust, which ranges from -1 to 1. And the second element, which is certainty, ranges from 0 to 1. All right, so here, based on the trust model, I will try to use a simple example to explain our idea of the Semiring-Based trust inference algorithm. All right, so let's say if we want to infer the trust relationship between node 1 and node 5, what are we going to do? Because node 1 and node 5, they don't have direct connection, then very intuitive ways, node 1 will ask her friends 2, 3, 4 about their opinions on node 5. And this relates to the trust propagation process. And also, when node 1 gets information from her neighbors, he will think of a way, she or he will think of a way to combine this information together. So this relates to the trust aggregation process. And I'll explain step by step. So for trust propagation, if we look at path 1, and we want to combine them based on like the Semiring operation, which is the multiplication process, then we can define a corresponding multiplicative operation. And the reason why I define it this way is because we want to make sure that the trust is not increasing in the propagation process. And also, you can notice that here, when the two trust opinions along a chain are both negative, the result of this inference process or the result of this trust propagation will return 0 or unknown. And the logic or the reason behind that is because we don't know the enemy of our enemy is enemy or friend. So it's very twisted. Yeah. So accordingly, for path 1, we can calculate the trust information. And also similarly, for path 2, we can use a similar way to calculate the trust information propagated along path 2, and same for path 3. So now we have already got information from all 3 passes. How are we going to combine these different sources of trust information? Well, it relates to trust aggregation process. Well, so we define this additive operation to do trust aggregation process. And it is defined this way because we want the opinion or information of the highest certainty to be considered in the aggregation process. So you will notice that if the certainty is, if we combine 2 opinions and one opinion has a stronger certainty or higher certainty, then we will take that opinion instead. And in this way, we want to use this way to handle the nonlinearity in trust formation. Okay, and based on this definition, actually a trust opinion from node 1 on node 5 can be aggregated and inferred. Oh, sorry. Yeah. All right. So here, after the short example I discussed before, this is the formal definition of our Semiring framework, which we call Distrust Semiring, because in this Semiring, we actually consider both trust and distrust information. And addition and allocation are defined same as before. And when the network is of large scale, we use first aggregate, then propagate scheme in order to depress the noise caused by long distance propagation. All right. So as we can notice here, because the aggregation or like addition process relies on certain information to reach result, so we really need certain information in our model. But in most cases, certainty information is generally implicit. So we formulated 2 certain models here to handle that problem. One is path-based and one is degree-based. So and for path-based model, the basic idea behind it is that if the 2 nodes are very far away from each other, then the certainty they put on each other should be very small. And the degree-based model has a logic that if a person is very popular and have many more connections, then his or her information is more valuable, so we will put more certainty on his or her opinion. And all the parameters in these models are configurable, which offers us the opportunity to run optimization and find out the best solution and to reach the best performance. All right, so far this is our base framework. And in order to further improve the performance, we introduced 2 additional components. One component is called iterative trust evaluation, which is a collective inference algorithm. And the basic idea is like, instead of doing trust inference independently, we consider it as a joint inference problem. And in each round, we get a result by running the algorithm, and then we put the results into the knowledge base, and then use that to further infer other connections or other edges. So here's a toy example. In this network, if you want to infer the transition between node 1 and node 5, and node 2 and node 5, then currently we only have 2 paths to use in order to infer tau 1, 5. And then the result can be shown, which is negative. And this is the initial result. But after this round, we have information about both, we have inferred information about both tau 1, 5 and tau 2, 5. So we will put them into the knowledge base and use for the next round. So in round 1 here, actually, there's a 3 paths between node 1 and node 5. And we use all these 3 paths to calculate the inferred trust. And now, based on these 3 paths, the inferred trust value between node 1 and node 5 is updated. And this is the basic idea of our iterative trust evaluation. And another component we introduced is related to reciprocity. And in scenario of trust, reciprocity means if I trust you, then you should trust me in the same way, which in general is not the case, right? But if we relax it a little bit and just consider the sign agreement, like if I trust you, you should, or you probably will trust me to some extent, then we can actually exploit this sign agreement information as an additional knowledge base for trust inference. And also in our evaluation stage, we noticed that the negative trust or distrust reciprocity is very noisy. So we only introduce positive trust reciprocity component in our framework. All right. So far we have three different versions: the very basic version, and the version with iterative trust evaluation, as well as the one with partial reciprocity. And here we use opinion dataset to evaluate the result. And here is the basic statistics. And we also found that the sign transitivity can be as high as 92%, and the sign reciprocity can be as high as 97%, which kind of echoes with the heuristics we use to formulate our model. And in this page, we want to compare the performance in terms of accuracy and coverage for different settings. And we can notice that when the test data set is smaller, then the ratio of training and test data set is very large, and the performance is generally better in terms of both accuracy and coverage. And also, if we look at the single graph, we can notice that when we have deeper hops here, the accuracy even the accuracy reduced a little bit. The coverage can be enlarged a lot. So there's a trade-off here, and as well as the computational efficiency. So the best choice in our case is 3-hop setting. And also here we want to measure the contribution made by additional components. And from these two graphs on accuracy and coverage, we can notice actually in terms of accuracy, there's 1% improvement. But in terms of coverage, with these two additional components, there's a 5% improvement, which is pretty impressive. And with combining the base model with these two additional components, we actually reach a very good performance for performance. And for error rate, it can be as good as 5.8%. And for coverage rate, it reaches about like 98%. All right, finally, not finally, but for parameter tuning, remember before I mentioned like certainty can have some parameter that can be tunable. And based on this result, we actually select this exponential model with a relatively small parameter value. And finally, we compare with other approaches in trust inference. And from this chart, we can notice that our approach compared to the graph theoretical models have a large improvements in terms of accuracy. And meanwhile, it has very good efficiency, computation efficiency, and interpretability. So as a conclusion, we propose this algebraic approach for trust inference. And we also run experiments on real-world data set to illustrate its accuracy and coverage. And this approach actually can be applicable to other applications related to trust in social network environment. So in one word, the takeaway is, so besides those machine learning, complex machine learning models and straightforward and simple linear models, there's a third option you may consider when you handle something subjective like trust. Thanks so much. Thank you.
Do you have any questions from the audience? So in terms of what you have here measured as trust, how are you measuring, how is trust represented or measured in this particular case?
So actually, in this case, we just use the opinion data set. And in that data set, trust is marked as -1 and 1. So it's just integer values. And it's binary, either trust or distrust. But in our model was developed based on a real value of trust. So trust can be varied between -1 and 1. Can be any real number between these two.
And do you think the fact that the trust can be represented as less than binary, what kind of impact that might have on your performance?
Well, so actually, because we don't have a data set that contains this kind of continuous trust value, so we didn't verify the idea. But since this idea was developed based on the real value trust opinion, and then it can be well applied in binary ones, so we would assume like the flexibility of this approach is pretty well. And in the future, if we have like real value data set, we will definitely verify that opinion, that hypothesis or that assumption. Yeah.
And also, you mentioned that one of the advantages is explainability.
Yes.
Can you just say a word about that?
Yes. So the interpretability or explanation ability means like our model is defined based on intuitive heuristics. So when you want to combine opinions, you always choose something that is more certain. And when you want to propagate opinions or get information from like people hops away, you're always trying to consider if the trust opinion is positive or negative. If along the chain there are several like distrust informations, then you won't consider those informations because it is too noisy and it's hard to determine whether enemy of your enemy is your friend or enemy. And actually, we did a small experiment on this opinion data set, and we found if the two opinions are both distrust or are both negative, then the opinion, and if we have, let's say, if A distrusts B, B distrusts C, and we happen to have evidence about the relation between A and C, and about 5% of the data shows that it's trust, and the other 50% data shows it's distrust, which means like basically if you have a two-hop distrust information, that is not useful in trust inference.
Okay, thank you.
Okay,
Let's thank our speaker.
All right, thanks a lot.